Let us do some preparation for going up theorem. So first recall this proposition which we proved in the lecture, transitivity of integral closure. So this proposition was, so say A is a subring of B, both of them are integral domains, and B is integral over A. Then B is a field if and only if A is a field. So an immediate corollary of this is the following. So say Q is a prime ideal of B, and then if you pick up a prime ideal Q here in B, you can always pull it back to another ideal in A which will also be prime. So this is easy to see. So say you have P over Q. This will contain, say, A over P, where P is precisely Q intersection A. So this will be an integral domain, and this would imply that this A over P is also integral domain because it lies within an integral domain. So since this is an integral domain, so this P is prime. So if you contract a prime ideal from B to A, you will get a prime ideal. So say Q is a prime ideal of P and P is the corresponding prime ideal of A, which you obtain by contraction. Then Q is maximal if and only if P is maximal. So this is easy to see. We just use this line right here. So now if Q is maximal, B over Q is a field, and if and only if A over P is a field, and this B over Q is a field if and only if Q is maximal, this A over P is a field if and only if P is maximal. So we are using the proposition, essentially just this line we are copying right here, and then we are saying that this is a field if Q is maximal and this is a field if P is maximal. So now we come to this corollary, which is incomparability. So again, A is contained within B, both of them are integral domains, B is integral over A. So say you have these two prime ideals, Q and Q prime. Q is contained within Q prime in B. So this is ring A contained within B. Q and Q prime are prime ideals in B, and both of them contract to the same prime ideal P in A. So both of them contract to the same prime ideal P in A. Then both of them are equal to each other. So if both these prime ideals contract to a single prime ideal in A, then they have to be equal to each other. So this is what we have to show. So first recall two facts. So this we have covered in the playlist on prime and maximal ideals, in particular in the playlist on localization and prime. So say localization at a prime ideal. So the purpose of localization at any prime ideal is to produce a local ring, this AP, with maximal ideal PAP. So this is the maximal ideal of this local ring. So local ring has a unique maximal ideal, and unique maximal ideal of this ring is precisely this. Fact number two is, so say you have a prime ideal Q in B. This will correspond to prime ideals in the localized ring, this BP, this QBP. So there is one-to-one correspondence between prime ideals in the ring and the prime ideals of this form in the localized ring. So the only condition you have to remember is that this prime ideal Q, when it is intersect with the multiplicatively closed set, this is empty. So this multiplicatively closed set is precisely where we localize this ring B, and this S is obtained from B. You subtract all the elements of the prime ideal P, and then you get this multiplicatively closed set S, and then you can localize B at this closed set. So there is one-to-one correspondence between Q in B and this QBP. Again, you can see everything in the lecture on primes and localization in the playlist prime and maximal ideals. So now let us prove this corollary. So first recall that you have something like this. You localize this, you get from here you get AP, here you get BP, and recall that localization preserves integral closure. So localization gives this, which is precisely this, and where this BP is integral over AP. So localization preserves this integral. Now the ideals corresponding to these ideals Q and Q prime, you have ideals QBP and Q prime BP. This is one-to-one correspondence, as we said here. So there is one-to-one correspondence between here and here. So if we prove equality here, then this will show equality here because of one-to-one correspondence. So what we want to do is we want to show an equality right here to show this. So both of them are prime ideals of PP and both of them lie over PAP. So again, because of one-to-one correspondence, these two lie over P. So it has to be the case that this lies over PAP and this lies over PAP because of precise bijective nature between QQ prime and QBP and then Q prime PP. But this ideal is maximal. This is the maximal ideal, and this we know from our first statement. So localization produces a local ring like this which has this maximal ideal. But here is the corollary that that ideal on the top is maximal if and only if the contracted ideal is maximal. So corresponding to these two, we had this contracted ideal, but this is maximal, so it has to be the case that both of them are maximal. So both of these are maximal. So both these ideals are maximal, but now they have to be equal to each other precisely because this BP is a local ring. So this BP right here, this is a local ring. So if you just look at this, this is a local ring. So local ring has a unique maximal ideal. So if it has two maximal ideals, it has to be the case that both of them are equal to each other. And because there is one-to-one correspondence between these and these, it has to be the case that Q is equal to Q prime. So both of them are equal to each other in the local ring because it has a unique maximal ideal, which in turn gives Q is equal to Q prime because by 2 there is a one-to-one correspondence between ideals like this and ideals like this. So now we have another proposition. So say A is contained within B, both of them are integral domains, B is integral over A, and say now you have a prime ideal which is sitting in A. So this is a prime ideal. Then there is a prime ideal Q in B. So we have a prime ideal sitting in the base ring. Then we can say there is a prime ideal sitting in the top ring. Then there is a prime ideal Q in B such that P is precisely the contraction of a prime ideal sitting on the top ring. So if B is integral over A and you have this containment, then you can always find a prime ideal sitting on top. So there exists some Q which corresponds to this P given here. So let us prove this. So again, so localization preserves this notion of being integral. So this will give you localization like this. Then this BP is integral over AP. So just like you have this containment, you get this containment. B is integral over A, you get BP is integral over AP. So now we pick up a maximal ideal in this localized ring right here. So it is always possible to pick up a maximal ideal in any ring using Zorn's lemma. So corresponding to this maximal ideal sitting on the top right here, the top ideal is maximal if and only if the ideal sitting under it is also maximal. So corresponding to this ideal, you find its contraction. So its contraction is N intersection AP. Always this is the contraction back in this ring, and this ideal is maximal. But this is a local ring. So this is a local ring, and so localization produces a local ring with the maximal ideal this, and this is a local ring, so it has a unique maximal ideal, and that is it. In fact, it has only one maximal ideal, which is this PAP. So this is a maximal ideal, it has to be equal to PAP, but this is in one-to-one correspondence with this prime. This PAP comes precisely from this prime ideal P sitting in A. So you can construct this Q as an inverse image of this N. So this Q is inverse image of this N, and obviously inverse image maximal ideals are prime. So inverse image of a prime ideal is a prime ideal. So this is how you get Q. So Q is nothing but inverse image of, Q is inverse image of our ideal N. So we have been able to find Q, and this square commutes. So this everything here makes sense. Now we describe the going up theorem. So say A is contained within B, both of them are integral domains, P is integral over A. So this is how we write it. So let there be these prime ideals. P is contained within P prime, both of them lie in A. So we have this containment, P is contained within P prime and both of them lie in A. And then we have an ideal Q which is sitting over P. So this Q is a prime ideal. So Q intersection A is P. So that is contraction of Q back to A is P. So Q is a prime ideal in P. So now this going up theorem says then there exists a prime ideal Q prime which sits over P prime. So there exists this Q prime which will sit over P prime. So Q prime in B such that Q prime intersection A is P prime. So that is contraction of Q prime back to A is P prime. So we have to show that such a thing exists. So first thing we do is from A we go to A over P, from B we go to B over Q. So we can construct such integral domains. So just modulo out the prime ideal Q here, modulo out the prime ideal P here. Now P prime contains P, so this P prime over P is a prime ideal. So this is a prime ideal. So on top of this prime ideal sits this prime ideal Q prime. So on top of this prime ideal sits another prime ideal. This is the proposition we discussed before. So let us recall the proposition by which we can find this ideal Q double prime sitting over this ideal P prime over P. So this is a prime ideal of this ring and this is a prime ideal of this ring. So the proposition was that A over B is an integral domain like this with B integral over A. So B is integral over A. So let P be a prime ideal like this. Then there is a prime ideal Q which lies in B such that P is the contraction of Q. So P is Q intersection A. So in this result here, instead of A we are using A over P. So this is an integral domain because P is a prime ideal. Similarly for B we are using B over Q. In place of P we are using P prime over P. So this is a prime ideal of this ring. So over this prime ideal sits Q. So over this prime ideal sits Q double prime. Now the inverse image of Q double prime in B. So this Q double prime is the prime ideal of B over Q, but then you can pull it all the way back to B. So inverse image of this Q double prime, you can set it as Q prime. And that will sit over P prime. Precisely because Q double prime sits over P prime over P. And this contains Q. That is how this is a prime ideal in B over Q. So this inverse image of this in B is Q prime which will contain Q. And this will sit over P prime. So now we discuss an important corollary. So say A is contained within B, both of them are integral domains. B is integral over A, and consider this chain of prime ideals like this, P1, P2 all the way to Pn. This chain of prime ideals is in A. So you have P1, P2 all the way to Pm all the way to Pn. So this is in A and the B is sitting right on top of it. So in another chain B you have a set of prime ideals, say Q1 contained in Q2, Q3 all the way to Qm. So till Qm you have, where m is less than n. And all these prime ideals sitting above these prime ideals because you can contract each one of them to get here. So contract Q1 you get P1, contract Q2 you get P2, contract Qm you can get Pm. But notice that this is given to us till Qm. Chain in B is given to us till Qm where m is less than n, and chain in A is given to us till n. So the corollary says that we can extend this chain from m to n. So we can extend the chain in B which is ending at m all the way to n. And the way to do this is that from Pm you can go to Pm plus 1 and then apply this corollary again to get another prime ideal. So P is contained within P prime, there is prime ideal Q prime sitting over it. So in this theorem we said there exists such a Q prime sitting over P prime. So from here you will have some Qm plus 1 sitting here, and inductively you can build all the way to Qn.